Okay, today we're going to go through different presentations from students today, and then maybe we'll finish up about what we're going to do the next project lab. I'll go ahead and assign that, and don't worry, that one's not due until March 19th.
Okay.
So you have time to finish what's coming up. But it's important you pay attention to what's happening because you're going to be using all these components to put together and actually build a single cycle processor. You came to me and said you wanted to build something. I'm delivering.
No, I want to build something.
Now?
No, wait. That was me.
I kind of said I wanted to build.
Let's go ahead and welcome our first speaker,
build.
Jackson.
What's up?
Is it Chris or Chris?
Chris.
Okay.
Yeah.
All right.
I mean,
Everyone
yeah.
come on, let's do it.
Okay. What's
All right.
up? Oh, hey PJ, how's it going? Welcome to my presentation. Yeah. So this is I had the adder as my component, but I didn't realize it was supposed to be in 32-bit. So it's an 8-bit. So imagine just 4 of these working together, and then we're good. It's great. So the functionality it's an adder for 2 8-bit numbers. And then it's implemented in structural Verilog model. So, and then the design I did is I had like a separate unit for the look ahead carry, and then like I just strung together like 8 1-bit full adders. So, okay, so here's the code for like all of it together. So, yeah. Ignore like some of the calculations for the gate delay in the comments because I changed it later when I realized I was wrong. But yeah, so we have 8 full adders working in a series like that. So, and then we have the separate look
And if
ahead
it was a
carry.
32-bit adder, what would be different?
There would be 32 full adders.
What else would be different about your code?
That would have a lot more of these.
Okay.
Whoa.
Yeah, so there's that.
What about your inputs?
The inputs, yeah, the input, it would be from like 31 to 0, and same for output as well, but there's always still just one carry out bit,
Okay.
the leftovers. So there's that. And then, so this is just the 1-bit adder code for just like 1 bit at a time. So you have, your A input, your B input, and then you have your carry input. And then so you have your answer, which is calculated here, these 2 XORs like this. So you have A and B, they're XORed out to this Y, and then so the Y from the A and B are XORed with the carry in, and then you have your answer. Voila. And then so yeah, so it would work with the look ahead carry unit. I had a generation output and a propagation output. It would generate a carry bit if both of these were a 1, and it would propagate the addition if at least one of those was a 1. So it would have the potential to carry, if a carry bit was passed in. So that's super good. Here we go. Here's the look ahead unit. This was the longest and the most difficult part, and that's a lot of stuff. So yeah.
It was great you did this, but I only asked for a standard adder. I didn't need a look ahead adder, so go ahead. This is
Right.
great.
Oh great. So oh cool. So I'm
You went
actually
above
doing
and
good.
beyond.
That's great. So okay, so the way you would calculate each, of the next, carry bits is, you would have, CI plus 1. So, C1 would be G0 plus, OR. It'd be G0 ORed with the AND of C0 and P0. And then you would just, iterate through until you reach the end, which in this case was 8. So, and you can see there's just increasingly more of this mess as you go down to C8 there, and that's just nasty. So we're done with that. And here we have the tests. And here we had the tests. I tested, I added some numbers so that way we could demonstrate, the carry bit working, and then just had a simple one here, and then I added like two of I had like two super large numbers together. So, and then here are the results. So this one, as you can see, worked out great. So you have 1, 0, 1, 1. So that's in binary. 3. Let's see, 1, 2, that's 3. That's 8. That's 11 plus 3. So then you would get 14, which is, I think that's what we got, right?
Alright.
I mean, it works out in the binary. I just can't translate them right now because I can't think. But and then of course, 1 plus 0 is 1, and that worked out great. And then so this one is 0f, 0f. No, or is it 1?
Alright, well, the purpose
Anyhow,
of this test case was to at least show that you can do basic addition as well as carry bits. Because
Yes.
11 and 3 have 1s at the beginning, so you need to show that you can carry those bits over. Okay,
Yes,
great.
exactly.
Go on.
So the issues, there were a lot of wires and ands. There was probably a more expedient way. I could have done what I did, but I didn't. So lots of wires and ands. And I'm not sure if I got the sign of it, like negative and positive, exactly correct. I don't know how I was supposed to deal with like 2's complement and negative numbers.
Well, does overflow happen? What happens when you overflow?
It would just go into the carry bit, right?
Did you test for that? Okay, that's fine.
I guess I should.
Keep going.
But I mean, if it works like the rest of it did, then it should have. But
Shit.
should have. Oh, that's a fun word. So the gate delay calculations for the look at. Why is there another one of those? Oh, I meant to add
You didn't
that
want
there.
to tell us the other problem.
It's a secret.
Yeah.
So I have like a series of parallel ands, like so like in series they would add up to 24 ticks, which was the longest part right there.
Okay.
Like that longest and right there, that is 24 ticks. So because otherwise they're like all of these are working parallel.
Okay.
So, and then after after the parallel ands, then the ORs can do their job, and then that longest one there
Right.
in C8 is also 24. So, and then the full adders each has a value of 4, and there's a series of 8, so 32.
Okay.
And then since these are both kind of working in parallel to each other, we're gonna like defer to that one. So we have a grand total of 48 ticks, which is when I did my tests. As well, I did 49, just one for good measure. So.
Now, in the code you submitted, did you put the gate delays inside of the Verilog?
Yes.
Okay, good. So I can look at it there. All
Yes.
right, great. Okay.
Yeah. So.
Wow. Okay. Well, any questions?
Yeah. Any questions?
I was hammering them, but
Actually, your Verilog code, like slide number 3 or something like that. You had an adder in there or whatever. What is it?
This one?
That one there. Oh, yeah, that one right there.
Yes.
Do you use the function for the adder in Verilog then?
No, this was just this full adder right here.
Mhm.
That's just that's this module right here where
right,
it's
you
just
call
the one
module
bit.
itself.
Yeah.
Okay, gotcha.
Yeah, that's how I did that. So.
And where did you have the module located when you were calling that? That was your test. That was your.
Yeah, like when I compiled it with iVerilog, I
right,
did
so you
like
did your one bit
I just
code.
like included everything, so it was like adder.vvp,
Right.
and then I had adder.v, adder.test.v, full adder.v.
So you had like about 3
look
or
ahead
4
carry
files.
unit.
You had
Yeah,
about 3 or
pretty
4
much.
files.
So.
Okay. Did you do an analysis of what the was it carry look ahead and just the carry sum tick wise would be different?
Yeah. Because this one is 48 and this one is 32. So.
Okay. Well, hold on.
Wait.
No.
Oh, so like if I did like a ripple carry
Yeah, ripple
adder,
carry.
I did not.
Okay. Oh, that's fine.
So.
I just wanted. All right. Any other questions?
But suppose.
Well, you didn't have to do a look ahead, so you're good. Yeah.
Okay.
Yeah.
Sure.
You went crazy.
Okay. Oh,
Any other
geez.
questions? All right, let's thank our speaker. I'm not super grading presentations. I'm just giving out notes. So
Okay,
here you go.
that's great because
I'm just giving notes.
I'm just giving out notes. Your presentation's more of a.
Did you get up there?
Did you get up there and can you actually speak English? You know, stuff like that.
Oh, God.
Yeah. I know. Thanks, Carla. Wow. Ouch. All right, who's next? All right.
You're gonna see simplicity.
It's okay, simple. It's
Did you
okay.
push it or
Simple
not so
wins
much?
today.
Oh, I did. It should be.
Or did you push it just now?
Oh no, I couldn't get my PowerPoint to push.
Okay. Well, do you have it on thumb drive? Oh yeah, these things.
Yes.
Those things.
Well, I tried sending that link. and it
Guess what
wouldn't-
I've run out of?
Oh no way.
No USBs.
Oh, there's one in the back. Okay, good.
There's one in the back. Wait, is there one over here too?
Uh,
There is. There's a keyboard.
Huh,
You have USBs
why?
on the back of your
Why is the
computer.
keyboard up?
All right, which one is
I
it?
don't know.
oh.
Oh my.
We're all. This is going up on YouTube for all to see.
Oh, man.
Oh, I have a question.
That should be at the very bottom then, whatever one I used
All right,
last.
we'll go into.
So the first way is what I'm actually sticking with now.
As soon as I got in the travel drive, it's right there.
It's not letting me. Oh, it's in media.
10 or
Whoops.
11 hours on it, trying to get to work. And then I was like, oh crap, and then I realized there was like structural that I could
Is that it?
run, which was like
Looks like
10
it.
minutes.
Yeah, that's it.
So I have both of them there.
I was trying to push it and I couldn't push it. So.
All right, let's go ahead and welcome our next
can't
speaker. I
get
guess we're not going to even
cheat
use this.
to run it all.
John.
And
Same background I did, except my screen.
yes, well, because it had the circuit.
Yeah.
That's why I didn't use that
Well,
one.
I chose the Mux. I thought, well, it'd be super complicated or something compared to the extender, and I realized that it's not as complicated as I thought. And reason being is, oh, is that light shining on there? Can anybody see it?
Oh, a little bit.
Oh wow, look at that. No, that's not the light. That's just your slides.
Oh, okay.
Yeah, that's.
Oh. Well, what is the Mux?
I might see it.
Thank you.
Better background. All right, go ahead.
Well, a multiplexer. What is a multiplexer? Well, we're just taking multiple inputs and putting it out onto one line. And that's why it's called a multiplexer, because multiplexing is just doing that. The act of taking multiple inputs and pushing it along a single output line at various speeds or different times. And so we take those. Is this projector where it's cutting off?
Yeah, that's probably because I'm using LibreOffice and you did this in
PowerPoint.
yeah.
Yeah, so-
that's why.
All right. So anyway, this basic gate is what controls data movement in our circuits. So, and then the more complex, yeah, it's definitely looking a whole lot different. The more complex, I give a 2x1. I just did the simplest one, but you have 2 inputs, 1 output, 4 inputs, and then 8 inputs. If you do this, obviously more complex, more gates. As you saw, as he had to do, like he had 8, and then you went to go to 32. Oh my gosh. I'm so glad I didn't choose that.
Wow.
I'm sorry. It was just like I didn't realize how simple this was. Really, when you think about it. I mean, generically, we have a mux. We have 2 inputs. We have 1 output. We have a selector. These are all over the place. Anyway, that's a selector input. And what we want is, if we have the 2 inputs, we want on our selector. If we have it at state 0, we want line A. If we have it high at 1, we want line B. And yeah, line B. And so it doesn't matter what's on line A. When we select 0, we take whatever's there. So anyway. Okay, then implementing that table, since we know what we want, in order to implement it, basically we're doing 2 ands. For our selector, we have 1 line come in for selector, but we knot our input into the first and we let it just go in straight into the second and.
Okay. Explain why we're doing that knot.
Oh, we're doing that not because we don't want to, as I said back over here, we want, when we have A coming in, we want, when we select S as to be 0, we want this AND to work. So if we have it at 0, then that changes it to a 1. So this side will allow the A line through.
Okay.
Yeah, that's the reason why we're doing it. If we're
Okay.
yes, and then reverse for the other side. Yeah, I was just getting to that. And basically, if you're doing a 4x1 mux, you'd end up as a more complicated 4x1 mux. You'd have 2 more ANDs, and then you'd have 2 selectors because you've got to address the 4 different lines that are coming in. And so you want to let it go. Let's see. Okay. Lab gate delay. Our lab specified what the gate delays were. So from the previous slide, we would have 1 NOT, 1 and 1 OR. So since NOT is 1, and is 3, and OR is 3, our gate delay for this mux is 7. It has to do with you have the NOT, an and the OR. You know, it's just,
Doing great.
I mean, so it's so simple. I mean.
No, you're doing great. Go.
Okay. Verilog code. Well, anyway, taking that code, same thing as like in lab 1. You know, you just these are your
Looks great.
ands and ors.
Yeah.
Sorry, we're just low on time, so we're good.
All right.
All right.
Once again, the table. So in checking the table, I have to check all possibilities. So let's say I know I only want A to come through, line A to come through when I have S as 0, and line B to come through when I have it as 1. So I still have to check all the possibilities when A is 0, B is 0.
Yep. So just
So
why
what's
did
your
you-
outputs?
Why did you choose to test everything as opposed to only a couple?
Because it always seems when I test the ones that I expect the answers to be correct, that something comes up.
Right, and
it
also,
could
you
be.
can test everything here. It's not like it's a huge. I mean, that truth table has some size to it, but it's not.
No, it's not like. Yeah, it's not like as if I'd gone to the 4 or the.
Right, yeah, right. Okay,
right.
good, awesome.
Yeah, it was easy. It was easy enough to do.
Great.
And then, of course, the test case. I started off. You do the registers. You call up the
Looks good.
problems, and
Yeah, there we go.
and then the module. And so the more complex one, I would draw for you, but you don't want the time. It's basically, as I said, 4 gates, 2 inputs. You take in the first 2 gates, you'd have your first select 0. You'd have a
Is there a
not.
diagram of this one?
I didn't do it. I can draw it up for you,
Okay, that's okay. Let's just keep going.
and that's it. I mean, really, my issues. Having trouble pushing the 2 program codes in the PowerPoint presentation to GitHub. That is my basic issue. It was so simple. The code was very straightforward. When I did run the tests, I got that table. I got the output I expected. When I won line A, I got whatever was on line A, whether it was a 0 or a 1.
Great.
And that's it.
All right.
Questions?
No questions?
No questions.
All right. Your code that you pushed, did you put the gate delays in it?
The dot 10, yeah, or whatever in the tests?
Yeah, yeah. Well, no. When you have the ORs,
Mm-hmm.
did you put the gate delays in there? Oh, I see I think I know what the problem is, guys. All right, here, hold on.
No, I must have read the instruction
That's
wrong.
fine. That's fine. Maybe we didn't explain it. But yes, good job. Let me go and explain to class what it is I'm talking about. Oh yeah, you probably want to take that out. Hold on. Let me
yeah, close me out.
close you out. All right, go ahead and take it. Oh no, it failed to open.
Why do we have that up on there if we're not using it?
I'm using it right now.
Oh, okay.
See, I started to do the 4 and the 8 ones and had all that stuff. And then
Okay.
wait a minute, he said just.
So when I was talking about gate delays, I wasn't talking about the delays in your test code. I was talking about the delays that you to put inside of your modules. So you know how you may have, what was it? You had an and. What was the and you had inside of the mux? All right, we'll just say y0, comma a, comma b. To put the delay here, what you do is take this and move it over here, 3, so that the delay is part of the actual module.
I had that in one of mine.
Awesome.
Actually, I think it might
So
be
you wanted
behavioral.
the delay that we had in the
module.
module when I said just so.
Yeah,
what
just
you
put the
had was
delays
that-
in your
so the
module.
not would have been in pound 1,
Yeah,
and
pound
whatever,
one.
and
You
whatever
got it.
Whatever you said on there, I was supposed to put that in the module.
Yeah, exactly.
Oh, I just did at the end. I calculated, so basically.
I understand. Yeah, I'll make it clear next time. Jackson, did you put it in your test code, or
I did not.
or did you? Well, I'm sorry.
But-
You put in your test code, obviously, but did you put it into the modules?
No, I didn't
Okay,
do that.
all right. So this
But,
is what I'm
like,
talking about.
All the individual, like I dumped like every single wire to my test code, so you could go through that and it would.
Well, if it's part of the code, because the point of this is we're going to be taking all your components, putting them together, making an actual processor, and if you put the delays in here, you actually see the delays going through.
Okay.
Okay?
See,
That's all.
in the test codes, we just had, here's display this, then give it a delay between each initialization.
Yeah, you got it. But that's okay. So,
I think my behavioral has one of them.
Quick question.
Just
If
one.
you did that for like an AND with multiple arguments, would that spread that?
No.
Would that multiply it, or would you need to calculate?
you would have to
the-
calculate. Notice that this
and
is
then
for
put
only
that.
2 ands, but if you
Right.
have multiple ands, you have to figure out how
So then,
those
if you
actually
did
laid
like
out.
y, so if you did y0, comma a, comma b, comma c,
C.
then you would put.
Yeah, that would
pound
require
6.
2 ands because yeah, you would need
Okay.
right.
Cool. Just checking. I just didn't know like
Wait, you mean
it would do that. Well,
Yeah, because if you have
I just
because right here you have this, where you have A and then B and then Y0. That's what you have up
Right.
here. But if you were going to add a C to this,
As another input.
yeah, the C would have to go over, well, the way this would work out is you put, this would go into another AND, this would go into a C, and then you have Y0. So then this would actually be a 6 and not a 2 because you have them in series, right?
Oh, wait a minute, because you wouldn't do, I thought if you did an and you had 3, oh, never mind. It's
Yeah,
not.
because it actually is implemented with 2 ands.
2 ands.
Now, keep in mind that if it went to 4, this is why you have to think about it. It's still 6 because what's going on is now you have C,
oh, that would probably
D.
change some of the.
and now it's still
calculations
6.
in mine.
It's just it's done a little differently. So
That would probably change some of the calculations.
But if I'm going from the diagram to the and, then I can figure from the diagram what my,
yeah,
what my delays
it just
were
required a
anyway.
little more thinking this time. It's okay this time. We'll try to make it clearer for the next class. But who's next? Carla?
Oh, that doesn't have to go low.
Just go under it.
Oh. Yeah, I didn't even see it. Thanks.
Hold those
Yeah,
up.
so, I mean,
Let's see, lab. Did you push it or is it on something?
Yeah, I pushed it.
Yeah.
like all those changes.
The only thing I pushed, actually.
Okay. All right.
All
Let's
right,
go
guys.
welcome Carla, our next speaker.
Hi guys, I also did the MUX, like John. Okay, so about MUX. They're basically data selectors, like he was saying, you just have a lot of inputs and one output. So I did cactus theme, because they have one base, and MUX have one output. Yes.
Oh, I see. Yeah, there's just one really tall column.
Yes.
All right.
Okay, so this was what I used for the 2x1 MUX, which is like his picture with the 2 ands that's knotted in an or. And this is my code, but this is before I added the gate delays to it. So it's pretty much like John's. Okay, and I also tested the select with the two different inputs, and yeah, you have 8, so tested everything as well. Then this is the 4x1, which I actually looked at. This was my long way instead of doing 2x1 MUX. So I just did that, and I did it. And this is like another way you could have done it, where you could have just did 2x1s, and then another one. Yes, but I didn't do it that way.
Oh, you
So,
did?
no, I mean,
Way.
I did my 8x1 that way, but I didn't do my 4x1 that way. Because I actually started with this one first, instead of doing the 2x1, so I did backwards, because, yeah, that's why I didn't do it that way.
Okay.
But that is my code, and see, that's when I was testing it, and I accidentally screenshotted the wrong one, but the knot is not really a 2, it's a 1, but we're just going to ignore that.
Why'd you start with the 4x1?
Because I actually started with the 4x1 because I figured that I was just going to be using, because I went on Google and I looked up a 4x1 MUX,
Oh, okay.
and this picture came up, and I was like, okay, well, I guess I'll start here, but yeah, so that's my truth table, which I'm not gonna lie, I did just Google 4x1 mux truth table. So here's the 8x1. So that's 2 4x1 mux with a 2x1 mux. And this one I did, I guess, a shorter, easier way, where I have the 2 4x1s and then the 2x1.
Blah.
Are you laughing at me?
The blah.
Oh, because you have to name it something. So I was like, blah. Yes. Yes. So this is my test cases that I did, and so this one was, I didn't know because I did it differently. So I just did I just changed one of them to give me back 0 to make sure I was doing it right. But I guess, yeah, so it worked. And so my issues is, like I said, I started with the 4x1 instead of the 2x1. The circuit diagram was terrible to look at for the 4x1.
Getting epilepsy.
And this, okay, so my screenshots were before I added the gate delays, but then after I added the gate delays, it messed up my test cases for just one of them. So I have to figure that out because that's supposed to be a 1, not an X. And it was working before I added the gate delays, so I'm pretty sure I did something wrong. But, so those are my issues. So, yeah, and these are my references. This YouTube video, check it out, guys. That was very helpful. Any questions, comments, concerns?
That's
You
what's
wear
lecture
the
notes.
cactus shirt because you have a cactus.
Yes, because I love cactuses. Cacti.
Cactuses.
Yes.
My black calls them like, ah!
If you added the gate delays, then when you did your test
Oh,
rate,
hey,
you
Joe.
have to increase the delay in the
Mhm.
lane.
Yeah.
That would be
That's the whole
one.
point of adding the delay, so that you would see that. Yes.
Oh.
So what did you
Wow.
do in your test code? When you did your test code, since you added gate delays, did you change in your test code the delays in between each input? That may be the reason.
But I thought with the gate delays it wouldn't matter. That would still have to be a 1.
Yeah.
See what I'm saying?
Well, if you have the gate delays, and then you're like, what's the total gate delay of your 4x1 mux?
14.
So, if therefore your test cases, you'd have to wait at least 14 for the correct answer to pop out.
Oh!
Yeah.
Thank you.
Yep.
You
But
have to wait 14 seconds at the beginning of your test.
14
but I'm pretty sure for my 2x1 I waited 7 yeah, and that just never changed. So
Right, that's, yeah.
yeah, okay, but so I'll push that code after
All
I
right. Now, another question, because if you looked at our processor, the mux is going to have to select from 2 inputs. It's a 2x32 mux. So how would you use your code in order to implement 2 32-bit inputs coming in and then just selecting one of them?
with more selectors.
Well, you're still only selecting between one, so you have one selector.
Okay.
Because right now, go back to your mux, picture of your mux, or name of the mux. Yeah, actual diagram. Here we go. So here you have what, N 0 through 3, and then what's down there at the bottom? Here we go.
Then I have the 4 to 7.
4 to 7. So that's okay. So you're selecting one wire from the 8 coming in. Right.
Right.
So what's coming in here is what I'm saying is you're going to have 2 wires. You're having it's basically 2 groups of wires because you're having 31 to 0 coming into another mux, and then another 31 to 0, and then you have one input selector because our processor is 32-bit.
Okay.
So you want to just select from one of the top, one or the bottom, because you might be going from register A or register B, or maybe the register A or the offset that was inside the instruction. So how would you implement this? And then the output, of course, is 31 to 0.
So would I not have to do it the split way and do it all together? Or just like the 8, like I did it with the 4?
So if you recall, or if you look up here, notice that you have 8 inputs,
Yes.
but only 1 is coming out. Up here, you're having 2 sets of 32, so you're having 64 inputs, but
Okay.
you're only selecting 32 of them. You're selecting either the top group or the bottom group based on your selector.
I don't know.
You don't know? Anyone want to help?
Yes, John, Mux person, friend,
Well,
buddy,
well,
telephone.
This is a 2x32, so let's go back to your 2x1 mux. Do you have the diagram?
Yes.
Okay, so do you have the other? Oh, whatever.
No, I don't. I just
Okay.
did this one.
Okay, that's fine.
Yeah.
Wait, 2x32?
Right, so there's two. You could call it 64x32 if you wanted to. I like to call it 2x32. Because remember, the by one is how many bits are coming out. But this one, you're selecting from two inputs, one wire, and then one's coming out. So how could you use this to implement this guy over here?
Je ne sais pas. No say.
No sense.
Yeah.
No sense.
How many cycles does it take to each one bit is one read through that?
Okay, so if, when approaching a problem that's big like this, try and break it down. How would you do it for just one bit?
The way we got it.
Yeah, it's the way you got it.
It's
So
by one for one bit.
yeah, you'd have, if this was A and this was B, you'd have A sub 0, B sub 0, and then you'd get, output sub 0. All right. How about for the next bit? Now you need to put the next bit. What would it be?
It would be the same thing.
Same thing, just below it. So how many 2x1 muxes would you need to do the 2x32 mux?
32.
Everyone see this?
Yeah.
And now, what would the gate delay be? Would it be more or less than this mux?
If you're doing it in parallel.
It would be the exact same. You'd just be consuming more area.
Praise.
Okay.
Yes.
All right. Any other questions? All right. Thanks, Carl. You're welcome. All right. Who's next? Sydney. Okay.
I did put references in my slides.
You did?
Yep.
I didn't see him. I'm sorry.
Yeah.
It was her last
Do you
slide.
want us to output to a PDF so it reads easier?
Yes.
Okay. I'm just gonna do that.
I did that too after the fact, but
Oh, is it? Did I just
yeah,
need to do
if
the
you
pool?
get pool. Yeah, because I wasn't sure because I realized that Mac does it in a PPTX, so it's like
So if I'd saved it as a PowerPoint, as a
PDF. Yeah. Sadness would not have occurred. All right. Let's welcome Sydney.
oh, thanks, guys.
We love you, Sydney.
Okay, so I did memory mostly because I couldn't remember what I was supposed to do, so I just picked one.
in memory seemed appropriate.
Yeah, so so it took a bit of trying to figure out what the heck to do for memory, to scrolling through the textbook and realizing that we could just do something as simple as a D flip-flop, because the functionality of memory components is you just want to store the state of something, and I got this from the textbook actually, is that all memory elements store state. The output from any memory element depends on both the inputs and on the value that has been stored inside the memory element. And so one of the most basic pieces of memory are flip-flops, and it's meant for signals, so you're just storing a signal if it's on or off. And so my implementation, or my design of the implementation, was a D flip-flop from the D latch and the gated SR latch, like we had for one of our previous assignments. And so this is my implementation. This is the D flip-flop code, and so it just starts off with a NOT, and then I call the D latch and the gated SR latch. And then over here you have NOT. This is the D latch, and you have NOT and two NANDs that are working at the same time, and two NANDs here as well. And then it goes to the gated SR latch, which has just two NANDs and two NANDs. So then when I tested it, I didn't test I don't, did I test everything? I think I tested just about everything. And so for the first two, because there wasn't enough delay, I guess it didn't give a it didn't give an output right away, but then everything worked out like it was supposed to further on down. And this is example of what I did for the flip-flop test case. And so I did the mistake of I thought we were supposed to calculate it and not put it in our modules. So based on the code, there was the not in the first one, that was 1, and then when you go to the D-latch, there's another not, and then there's 2 nands that work at the same time, so it's only 2, and then 2 nands again, which is 2, and then gated SR is the same thing as here, so I just added it all up to be 10 seconds or 10 ticks. And in terms of issues, it was mostly just realizing what the heck the memory component, like what we could have done and used, because I was stressing out and didn't know exactly what was supposed to be used for it, and to find out it was something as simple as that, I was just like, okay. So.
Oh, wow. Okay. Well, any questions for our speakers? Speaker, sorry.
It's okay.
There's only one Sydney.
Yeah, I said speaker.
It would be pretty bad if there was 2 of me.
Yeah, I couldn't handle that.
Okay, so wait, no,
On the code for testing.
Yes.
Well, what were you testing? Were you testing to make sure it latched?
I was just testing that to make sure I got the signal correctly. Like, so. Okay, so it only ever changes values, I believe, when the C and D. I'm trying to think. Okay, so it only changes value when the control is on versus when it's off, and then it only changes to a 1 or 0 depending on what D is. And so that's what I was just testing, is I was saying, okay, control's on, it's off, it's on, it's off. And then I was changing the value of D every now and then to show that, okay, if it's off, it'll stay the same. If it's on, it'll change. And then if it's off again, it'll stay the same. But then when it changes, it'll change the value. So I was just kind of alternating through to show you that, yes, it changes, yes, or no, it doesn't, and all that.
Alright, so this is with the D flip-flop. Now, with the data memory, you're supposed to store 64 kilo words. Did you implement that?
I did not.
Okay. Did anyone else have memory?
I did, but I did mine completely differently.
Okay.
Yeah, she did something different.
Right, because this is with a single flip-flop, which would be, which would be part of the register file. The memory is going to be a huge bank of memory units. So, okay, so if you're going to implement the memory bank with a lot of D flip-flops, how would you go about doing it?
To do it with D flip-flops.
Well, let's go ahead and step back. How many bits does your flip-flop hold?
I think it only holds 1.
1. Okay, so first off, how would you hold 32 bits with your D flip-flop?
I'd probably just
Have a whole lot more.
yeah.
Put a whole lot more together. Okay. All right. And now that you have your 32-bit flip-flop, what would you do for a data memory? Because it's going to have an input for an address and a date and a value to be stored, and then it's going to have a wire for selecting either read or write.
Okay, so read or write, address, and the data to be stored. I feel like the read or write is just a simple whether like
It's
on or off. So you probably have a variable for that, but then for the address you could to figure out like where it to figure out where it's exactly stored, you could probably just send it through its D not D flip flop. Trying to think.
Let's go ahead and step back. It's got to be 64 kilobytes of words. Each word is 32 bits. So how many D flip-flops would you have to store?
For 64 kilobytes for 32 bits?
Yeah.
A lot.
64 times 32.
64 kilos. So 64 times 2 to the 10th. 32-bit flip-flops is how many you would have to create for this.
Right.
How big would that be?
Really big.
Really big, right. So,
Just.
yeah, part of this, I guess it's good we showed this, because part of the memory is to show that if you try and implement memory with flip-flops, it's not practical at all.
Right.
So hopefully y'all did it differently, whoever did memory. Good.
Yeah, after 10 hours.
10 hours, all right, great. So, hopefully we'll get to that. And then, did you put in your delays for your test cases?
I did not because I got confused with that. That's when I did it. I thought it was just calculating it out.
Okay. Oh,
So,
that's right.
Yeah.
We need to specify that more.
Because all I saw that it was calculated. I didn't see that it was supposed to be put them in the.
Towards bucks?
Yeah.
Yes.
Do I do all I'm supposed to do?
Yeah. So, make sure you at least implement a data memory and implement instruction memory, okay?
Okay.
All right. Any other questions? No other questions? All right, great. Let's thank the speaker. All right, who's next?
I guess I can go next.
Okay.
Since mine has to do with hers as well. You'll have to read both.
Okay.
I did a PDF for you.
Yes, thank you.
Hi, how are you?
I'm doing great.
Yeah.
I also did the same.
Yeah. Circuits,
So,
yeah.
3 people so far have done the same.
Did y'all choose the same background?
Yes.
Really?
Yeah, that's
Yeah.
I got a PowerPoint, so
It was one of the first ones that popped up, like when I was starting it, and it's like, oh, pick this design. I'm like, okay.
I don't know how to fix that. Don't choose the same background as your teammates. I don't know how I can. I don't know how you would know.
No one used the circuit background.
All
Pick your
right.
favorite plant. Yeah, that works.
All right, go ahead.
I'm Caitlin, as most of you know. I chose memory. So this is basically some diagrams on how memory works. You have their address lines, you have the control lines, which show there's clock, which kind of controls how long each thing is, or it flips between, I think, 0 and 1. I can't remember what CS stands for, but then you have all these control lines that basically tell you if it can read or write to itself, or if it's just reading. And then that's just, again, another diagram for this pretty fun thing. So I had to research a whole bunch of different ways. I ended up picking behavioral. I actually also did D flip-flop at one point. And then I realized this morning that I could do the way I originally did. So mine is using, it's an implementation of RAM, so random access memory, because doing RAM took long enough, so I didn't want to do ROM as well. Because I had, yeah, I had multiple ways of doing it. At one point I had actually both of them, but I couldn't get it to work. Finally got this one to work, so I was happy enough with this one.
All right.
Yeah, working on it for 10 hours kind of frustrated me. But yeah, so it has the inputs of whatever address you want, the data, whether or not you can write to it, so that is either 0 or 1, and then the clock timer. And the outputs are the data that can be read. And here is the start of my code. So this is just the basic code for the RAM itself. So you have, which is kind of hard to see since it's the black, but so you have the parameters, you have whatever the inputs are, which are all the inputs from the thing. If it can be read, it has the reading. This is really hard to see with the blue.
I wrote that down.
Yeah. Well, I took it from my Vim, so next time I'll do it actually from like Notepad. But yeah, so it's just taking and reading it or writing to it. That one's to write to it, that one's to help read. This is the actual implementation. This is basically all like setting stuff up.
If you, do you have the line up there that shows how you, the structure where you stored all the memory values?
Maybe? I can't read it. So, I think that's what this one is.
Can you write it real quick on the board? Because I can't read it either.
I can't read it from here. Let me grab my computer. So I can read it from my computer. It's, yeah, it's really hard to see. I need to change my color settings.
Yeah, I can't even read it. I'm not staring right at it from 2 inches away.
Film design. Okay. Okay. I think. Well, I have the parameters. I think it shows it better in my test cases, but
Oh, well, if you can go to the test case slides, maybe that'll help.
yeah.
Fast forward real quick. No, I don't think that helped.
Not really.
No, alright.
And I don't know if this is a 32. I think at one point I had it as a 32, and I don't think it is right now. Hold on. Oh, it is. I think a 32-bit. That says 32. The rest of it says 4s and 7s. So, but it's kind of hard to see. But so basically, it has the all the inputs and stuff. It's setting up the registers. They're 4x0, which is the range. Because memory's stored with arrays, which is I found kind of interesting.
Yes. That's what I want you to write on the board so they can see how that's done.
Yeah, I can do that. But here, I'll just write one of the test case ones. So register. Where's the register? Forward. So it's an array called address write. That's where it's writing to.
Okay.
It's a register.
Okay.
So it doesn't work with wires. Tried that too. I had an issue.
Behavioral.
Yeah. The one that I had to have as a wire is the data read, because it's the output.
Yeah, that makes sense.
But everything else is in registers. And then so you go down and you have, yeah, this is the test cases. Go back. So this is writing to a spot, which is my address write, and it's inputting the data.
Yeah, and explain the always block to us.
Okay, so always at the positive edge. So it's basically you either have positive edge or you have negative edge. And from what I understand, most of mine all have positive edge. I did have, I think in my test cases or somewhere I had something with a negative edge.
Okay.
It works weird. But pretty much everything, it's kind of where you want to start. Is kind of how I figured
So
out.
in other words, you have a piece of code in this always block. That you have code between the begin and the end of this always block.
Yeah.
When is that code executed?
Whenever you're at the end, like the positive area of the array,
The positive,
think. Or of the
positive edge of what?
the clock.
The clock, right?
Yeah.
So when the clock rises,
Yeah.
you execute this code.
Yeah,
There we go.
yeah, that worked. Tests. So I did a couple of different test cases. I think I did like 3 or 4. And so basically it goes through, it sets it all up. It's pretty much all of this. This is setting up the first test. So you're saying writing to it is 0, which means that you can't write to it. It's basically a false, so you can't write. Write enable. Actually, that's for the clock. Clock starts at 0. Write enable is 0, so you can't write to it. The first address to read to is 5H1B. Addresses. I kind of looked up a bunch of random addresses, but this is the one that I found in the code.
Okay.
The other ones are kind of iffy.
So
but
what did you test for? You tested for writing to it and reading from it?
yeah, writing to it, reading from it. So it does that. So the first one, you turn write enable on. This is to write to it. The first part is reading from it, so it's seeing if there's anything there first, which of course there's not because you haven't put anything to it yet. And then you have the write enable turned on, so you can write to it whatever data you wanted, which is 8HC. What's that back? 8H. Let's go down to that on mine so I can actually read it. Yeah, C5. So C5 is what you're inputting.
Okay.
Yeah, the 8 apostrophe H thing was kind of weird.
That's 8 bits. You're gonna explain it in hex.
Yeah.
Yeah. All right,
Yeah.
Keep going.
So the C5, and then you toggle the right, so it'll
Okay.
toggle clock right, and then you turn write enable back off.
Okay.
And then you read from, you toggle it on to read, so it'll allow you to read it. And then you read from wherever you want. Again, more testing.
Okay.
Just the same thing, just different
All right.
inputs. So first you have no data there, so you don't have to put anything. So you turn it on, you write to it, and then you read it, and you have the C5 that you wanted.
All right.
And then
looks good.
again, write 25 and then D6. Yeah. Issues. Trying to find which one works. Because I tested, I think, like 5 or 6 different ways to do it. Which is why it took me 10 hours, and I couldn't get any of them to run because there's like little errors every once in a while. But so that was fun. And then I also tried the D flip flop, but I kind of like this one since I worked on this for so long. And then behavioral. So how behavioral works, it shows kind of the abstract of how it works. So examples. You can control the timing using my clock variable. Shows how the process running, and the clock goes between 0 and 1. So
And the behavioral model is where you have that always block.
Yeah.
What's the big difference? Yeah.
and then sources.
All right.
Lots of sources.
Oh yeah.
Ta-da.
Okay. All right. Any questions?
Yeah.
So quick question. You have your address right as 5 bits. Why is it 5 bits?
Because that's what the code had.
That's what the code had. What code?
Yeah. The code that one of the sources I used.
Okay. So, all right. If the address has 5 bits, how many address slots can it reference?
5. No. Maybe.
2 to the 5th.
Oh, that's a lot.
Well, no, that's only
32.
32.
Yeah.
And we're gonna have a 64 kilobyte memory.
So I'd have to.
How big would that have to be?
I'd just have to change that to be bigger. I think at one point I might have had it as 0 to 31.
0 to 30. Okay, so that would be.
They just hold a whole bunch.
That would be 4 billion.
Yeah.
But we want 64 kilobytes. So how many bits would that be?
8.
8
No.
would be 256.
Oh, so less than that. So
Well, no, we want 64 kilobytes, so over 64,000. 8 would be 256. 2 to the 10th is 1,024. So then you need to add another. How many bits? Anyone? Bueller? I mean,
62,000 and some change.
yeah. Just change that number basically.
wow, that's the first thing. All right, so 16 bits.
Yeah.
Right. 0 to 65,536 or 35. All right, so that would change your address in, but what about your memory? Would you need to increase how much memory you have in there to count?
Probably yeah.
Okay, so
So you
those
can
are
hold
the
it.
two changes you're
I just have to change where I had the
Right.
all the registers and stuff.
So make sure you get that in. You haven't. By the way, I'm telling you these things because you have until the end of the day to turn in the code.
Yeah, and it's so 32. So I just got to change all
Alright.
those things.
All right, let's go ahead and tinker once more. By the way, guys, I'm just writing comments for improving. You're doing great. I just, I only have time to write down certain things, so
So change all the registers.
don't feel bad if I only have semi-negative things to say. So who's next? Were you going next, PJ? All right.
To 32.
Yeah.
That's that first one bit ALU with that RPG.
Whoops. Let me actually run LibreOffice. All right, let's go ahead and welcome our speaker.
So I did the ALU and adder, and so first things first, ALU. It got messed up a little bit because I use PowerPoint, but it's ALU stands for Arithmetic Logic Unit, and it performs 3 tasks, or a basic one performs 3 tasks. It performs and, or, and addition. It takes 3 things: your 2 inputs, which are A and B, and then a carry in. And it outputs any one of the and, or, and addition, and then it also outputs your carry out. So you've got 2 outputs in a typical ALU. With Jackson, he had a full adder, a 1-bit full adder. A 1-bit ALU also requires a 1-bit full adder. and it's an additional module in and of itself. And it requires the same inputs, and it always outputs the same two things: carry out and sum. I implemented both using the Verilog structural model. Like I said, full adder is a standalone Verilog module, and it's a separate file, fulladder.v. A typical implementation of an ALU has it output one item of the and, or, and addition. My implementation outputs all three because I felt that was the best way to show everything that it did, and it was easily readable, easily understandable in my test cases. With my testing, I tested separately the full adder and the arithmetic logic unit because they have the same inputs, A, B, and carry in. For each of them, there's 8 possible combinations of inputs, and it's these 8 typical 8 because they each have 0 and 1. So that's I tested them both the same way. So this is my full adder implementation. This is hard to see, but I did include the gate delays in the code.
Okay.
So.
And did you just test every possibility?
I did.
Okay.
So I included one test, but it's just 8 of these.
Okay, sure.
So I mean, like, my screenshot shows 1,
Okay.
but this file has 8 in it.
Okay, that's right.
So this one's just 0, 0, 0, but it outputs A, B, carry in, carry out, and sum, and this is for the full adder. This is the full adder implementation. So with this, the way I calculated the gate delays is I added up all the gate delays, which added up to 30. But when I was listening, some of them would run in series. Is that correct?
Or parallel.
Some of them would run in parallel. So there's a set of ands here, and those would run at the same time.
Okay.
Is that right?
I can't see your code from here.
Okay.
Yes, there's a lot that can be happening in parallel.
Okay. So there are 3 knots here, 3 ands and or, 4 ands and or.
Okay.
So I believe if these ands run, if the knots run in parallel and the ands run in parallel, the ones that are running at the same time, it would be
You just take the longest path.
yeah, 1, 4, 7, 10, 13.
Okay.
It's 13 ticks for this one. So this is my arithmetic logic unit. So here, these are the 3 tasks it performs. It performs the AND operation, which is stored in operation 0, the OR operation, which is in operation 1, and then it calls the full adder, and that's where you get.
Now, is it AND or NAND?
It's AND.
AND, okay, yeah, it does a NAND.
It does a NAND.
Okay, so yeah, you just put a little in front of the AND.
Okay.
Just, yeah.
And then so the full adder is how you get your sum and your carry out.
Okay. Now, how do you select between, because the NAND and the
So in my implementation, what I was saying is that a typical ALU would have a mux selector, and it would
Okay.
output one of them,
There you go.
but my code outputs all 3
yeah.
things. So always.
Okay, and then so to make this fit with the code in the project, you just have to put the ALU at the end. I mean, a mux at the end to select which one you want.
Right, and so you would have an operation as the operation as an input,
Okay.
and then it would have one output and your carry out.
Okay.
And mine has all 3, the and, or, and addition, and then your carry out at the current moment.
Okay. Oh yeah. Our project doesn't do ORs. It just does an and add. So you only need 2. I'm just trying to simplify this.
Okay.
Yeah, go ahead. You're doing great.
The potential issue is the one that
You are, guys. I'm just trying to. We present these because I know it's confusing. Go ahead.
The potential issues that I had, it was the one main issue was how to determine what the desired operation is. So the reason I chose this implementation of an ALU, which has and, or, and then an addition, is because that's what's in the book, and I was doing research and found that in the book. So with this, you would really want your carry out output, and you would want one of your operations. And mine outputs all 3 operations in your carry out. So in the situation where you had a NAND and then the additions, the sum, you would want a selector to choose one of those instead of my implementation of outputting both. So that's my potential issue, is to the issue that I have is that I don't have an operation wire as an input. So having an operation wire as an input and checking to see what the desired operation is, and then outputting the desired output would be the next step in this. So my gate delays, I added up everything in mine, so it was 30 gate delays, and for 30 for the full adder and 36 for the ALU. But like I said, with the ones that were running in parallel, this would be 13.
Okay.
So this would be 3, 3, 13, which would be 19. And that's pretty much all I have.
All right, let's any questions? Well, so hold on. I always get questions. It's okay.
No escaping.
Y'all doing great, guys. Just I don't know. Wow. Okay, any questions for PJ? All right, so this looks like it's good for a 1-bit ALU, but our processor is 32-bit.
Mhm.
So how would you extend this for 32?
You would have 32 of them.
In series or parallel?
You would have them in. Ooh. I don't know. You would have them in series, I believe.
Well, so the question is, if you do 32 of them, can they all happen at the same time for each bit? Because you're going to hook up each bit from the 2 inputs to 32 individual.
I don't believe they can happen at the same time because you've got a carry out.
Right. So you have.
They have to happen.
Okay, right. Because you're
They
doing
have to.
carry out internally. Yeah. So you'd have to do them in series. Yeah. Okay. I see what you're saying. Yeah. Because if you do the ripple carry, they would have to be in series. Okay. Yeah. That makes sense. So okay, great. And then what would your gate delay be? 32?
It would be 19. Oh wait.
If you had 32 of them, you're saying there had to be
Yeah,
a
so it'd
series
be-
because you're doing
it
ripple
would
carry,
be-
which is correct.
19 times 32.
30, or yeah, right. You got it. Good. Which would be very significant.
Yes.
Okay. Great. Any other questions? All right. Good job.
You got the most star student. You star student. And then I have my stuff in my coding bin, so I just have to note that.
You don't have a presentation?
No, I do.
Okay.
I uploaded it, so to GitHub, right?
Oh, then I will do a pull. I like how everyone does it last minute. It's amazing.
Well, I was gonna have you just go to my portal.csu.
No, we're not. That's
Yeah,
way
I
too much.
figured not to
Way
that,
too much
so.
work. Way too much work.
Not in my code too.
Oh, it does a.
I'm gonna have to like exit the presentation.
Oh, you're gonna have to look at your code. Do you know how to do this? You do Control Alt and an arrow over.
Oh, that's fancy.
It is, well, sure. You know, Linux has only had this since the 80s, right?
That's fancy.
Let's see. Was it lab 3? No such file. Oh, probably because we should.
Not in me.
Whatever. Man, these are lies. Oh, it's in the register file? Okay. So which one is
so
it?
I'll have V and test V, or just register file, register file. Both.
Both of them?
Yeah, those
I don't think I can do both of them. GVIM's not that smart. Alright, so then you do Control left arrow, and then right arrow, left arrow. Okay.
Control Alt, right?
Control Alt. Yeah.
Okay. I did the register file, and you guys also
Same.
can't read it, so.
Note to self, don't
I-
use the blue gradient.
So, put that fly in. So this is the register file. These are your registers. It's a 4x8 register file. So you have 4 of them. Your data goes in here, and then so just know that for now. These are your decoders. This is for the write. So you put in your write address, and then you do your write enable. So either a 0 or 1 if you want it to write or not. If you don't write it, then it's just gonna like read it through the read address thingy. We'll just spit it out here. What else? I mean, that's pretty much it. This is the read. So you put in a read address, and then you enable if you want it to read or not. And then it'll read from here, the tri-state buffer, down with your data. You know, it's just reading, and writing. You know.
We haven't talked about tri-state buffers. What is it?
They're just so what you have like your input, and then you have pretty much a selector to high impedance or impedance. What is it? Impedance? I think it's impede. I don't know. And then whether it's activated or not, it'll go through, or it'll spit out
I'm glad this is college.
Impedance.
It's not.
Hey, I'm not here to do English, you know. That's not about me. So here's my code. All right, so I did behavioral, structural, behavioral model, structural. The behavioral model.
Once you do behavior, it's all
Yeah.
behavioral.
So here you can see I have my address, address to write to, then your enable write, your data, your 8-bit data. Then this is like your registers. So I have a 8-bit register of 8 of them, I think.
Does everyone see that? No, you got it right. But does everyone see that?
Yeah.
So on the left is how many of the registers you're going to have, and each register is going to contain 8.
Oh.
It's an array,
Flip-flops,
pretty much.
essentially.
Yeah.
So that's
Or a
how it's set
flip-flop.
up.
So the brackets with 7 to 0, that means that it's an array of 8 registers.
Right. The one on the left says it's 8 of whatever we're about ready to create, and the type is register, and each of these has 8 registers, essentially 7 to 0. So yeah, there's 8 registers wherever register is 8-bit.
So this is the output value I have, and it's 8 bits as well. This is my always block. I don't really know what an always does, but I just kind of
You just copy.
copied that part. So then this checks if the enable write is enabled, it'll put the data to the register address, and then if it's not enabled, then it just spits it out to the output value.
Okay.
Then it ends. And this is my source. I just put that there. So yeah.
You have Blankscape.
Yeah.
That guy.
You know him?
No.
Oh, you don't? Okay. Then my test cases. So I gotta. You just want me to go to the terminal and.
Why don't you just do file open?
Oh wow. That is something.
Don't open the VCB.
You sure?
It doesn't look pretty.
Okay, so this is my test case. So the first one, let's see so I have address 1 or register 1. I then put the value of register 1 into register. So I put the value of 2 into register 1, and then I tell it to write.
Right. So what are you testing here? You're testing reading and writing.
Yeah, I'm testing writing right now, and then this would display 1. Then I just test like if you put a data type in here and you try to write it, it doesn't write obviously until you call it to write, and then it outputs
And
it
then you
here.
get it back.
Yep.
Okay.
So
Great.
that's all that. Issues. I didn't have any. It was pretty
Had
easy.
no issues.
It was really easy.
All perfect.
Yeah, 100. So,
Uh-huh.
yeah, that was great. Behavioral model because that's just what everything was online. I said, as in the words of Dr. West, do it this way or sadness will occur.
Yep.
You don't need an explanation why. Just don't do it any other way. Stay tuned for Jonah's presentation where he assigns you all homework. So
Wow.
I hope you still have that in there, right?
Maybe. Oh, okay.
Okay. So that's my presentation. So.
All right. Well, first let's thank our speaker.
Yeah. Not gonna clap. Wow.
Now, did you look up how much? Oh, I'm sorry. Anyone have any questions? Yeah, just take care of it.
Yeah.
Did you look up how much delay there actually would be in this register file?
No, I didn't.
No. Okay.
No.
All right. I understand. That's fine. Now,
You can do it real quick.
So you didn't have any problems with your tests when your delays of 5 that you put in between?
well,
No.
yeah. Since it's a behavior always block, it happens in less than 1 tick.
Yeah.
I just did the 5 because
There was a problem I had earlier where
Great. Well, you don't have a clock in there, do you?
no, there was a clock option, but I didn't know if I would just put a 0 or 1 in it, so I didn't kind of mess with it. I just did the whole
Right.
always
So if you
block.
added a clock, what would be the purpose of the clock?
To have it be done in 1 cycle.
Great guess.
Yeah. I don't know, to be able to time it, I guess.
Time it. Okay. Yeah,
Just
'cause you
see how
wanted to
fast
only
you-
write at a certain point.
Yeah.
And basically at the end of your clock cycle. So when you start to the edge rises, you want to make sure everything's written to it by the end of that. And then same thing with reading. Well, actually, with reading, you're always outputting it.
I saw that you can also have 2 reads. I think that's kind of the standard.
Yeah. That's. Did you have 2 reads in yours?
No.
No. Okay.
No.
You don't have 2 reads.
I just kind of had an output value.
So
for
what?
one
So
read.
That was one difference between what you presented and what we need for our project, 'cause we need 2 read
Two
ports.
reads.
What's the other difference?
You just so like having another read. And,
Right,
like,
you have
the-
another read port.
Yeah, so you have another read and then another
Sure.
address
Right, so that's the first difference with our
Yeah.
implementation. What's the second difference here
for
between what you did and what we need?
clock.
Clock? Okay,
Yeah.
sure,
Clock.
What is the bitness of our processor?
32, right?
Right. How wide are your registers?
8.
8.
So maybe multiply that by like 4. Yeah.
Go back to your register code. Yeah, go back. Yeah, let's open that up. So what do you need to change here?
So I need to change the 8-bit register to a 32-bit register.
Yeah,
Add
so
another
which part
read
of that
file.
would you change?
So this right here.
No, that's the how many registers?
Oh, this right here then.
Yeah.
Yeah. And the data type because we're probably
That one, and what's the other location?
the address.
No, the address is fine because we're only selecting.
Oh yeah, so the data type, like I said,
Right,
right,
right there,
the
that's
32,
correct.
Yeah.
And
Oh, the output value.
yeah, go down 2 more. There we go, and that one's
Yeah.
great.
Easy.
Just change that to 31.
And then
Yeah. Well, don't do it now. But. Okay. Good job. Okay. Now, who's next? Melina?
Don't read code. Take better back.
Yeah, I mean, whew.
Hey, it looked good on my computer, so that's all.
It looked great on your computer? Yeah, that doesn't mean anything.
It was really blue on here.
All right, let's welcome our speaker, Melina.
How do I go to the next slide?
Just the arrow.
Arrows, yeah.
Yeah, just press the arrow.
Okay. So I chose to do the decoder and sign extender. I apologize. I didn't have time to actually implement sign extender.
Okay.
So, yeah, what is that? So decoder functionality, it's part of the control building block of a processor. It takes n inputs and produce the output. Yeah. And then the output, no, hold on. Only one of the outputs will be true for any input combination.
Right, so it's going to
Right.
activate one of the blocks.
Yeah, right. I'll just briefly explain it. Sign extension unit, that's compute building blocks of processor. And then it's useful when compute unit is wider than data. I got the example here what it does. So like it converts 4 bits number to 8 bits and the 8 to 16 just kind of extends, but it holds the same value. That's a lot. Okay. I did the 6 to 64 decoder. This is the diagram for that. Takes 6 inputs from here to there, and then 64 outputs. I didn't even list all that. Inside of
Sorry, you got 6 inputs, right? 64 outputs, great. So you have you use 9 3 to H decoders.
yes.
Okay.
So like one of them produce.
One moment. Let me take a break before sadness occurs and the whole thing goes down. Apparently I didn't plug in. Yeah, that would be funny.
Oh.
Right in the middle.
It would happen, if anybody, it would happen to me.
It would happen to you. So excuse the interruption. There. All right, now we're good.
So I have 9 3 to 8 decoders inside, and then one of them produce enable pins to other 8 decoders, and notice that like all the 8 3 to 8 decoders work in parallel.
Right, so you have 8 of the 3 to 8 decoders are what actually activates the final line. Then you have
Yes.
basically a master 3D8 decoder that selects.
Whoa.
Oh, is it not plugged in?
Hibernate the system. Shut down.
All right, main thing turned on. All right, now it's charging. There we go. All right.
That went from yellow to red real quick.
There's no battery life. All right, go ahead.
Alright, so the first 3-day decoder, I didn't really have to put the nibble input in this, but like I just wanted to organize this way since other 8 have, you know, nibble inputs. And here's part of my code. It was actually like long code, so like I didn't want to put everything in there. But so this top part, it's all this line of AND gates, 8 of them, were I coded in parallel, and then these are the second base line, and then third one, it actually produces the enable output. This is for the first first 3 day.
3 day. Is this for all of them or just for the first
It's just first one.
Okay.
And then actually I don't think I put the other 8 other 3-8, but kind of works the same way, just the variable or the module's different. And the way it works is, example, if we had inputs like this, the first 3 numbers is going to be taken care with the first 3 to 8 decoder, and so this is going to be decimal number 2, so it's going to enable the enable to this one. And then the lower 3 number is going to actually determine, like you said, which line to activate.
Okay.
And then there's other example, but same thing. So I actually did 64 patterns of test codes. It's in the GitHub. I mean, yeah, it's in the code if you want to look at it. It's like 2,000 lines of code.
Yep.
So yeah, it was a lot.
But you know, once you get it done, you tested it all, right?
Yes, I did.
All right.
Thorough testing.
Thorough testing.
Yes. And then this is just one of the test cases. I actually did put the ticks in the actual codes too, but it's going to, I'll explain it later, but it's going to add up to 20, so I put that. And there's input 30, 61.
Okay, great.
And then this is how it's going to look like in the codes when I run it. This is going to be the input, and then notice like there's only one. Other than that, it's going to be 0 and it's stable. And yeah, that one's the same thing. 60. It's only this part that's 1. It's just hard to see, I guess.
Yeah. Well, no, I think your left is. If you look at the top, you have 30, and then right under that, you have all the input bits as on. So I think that was just a typo with all.
Oh yeah, I think so. Yeah.
Yeah. Okay. Good. Because the other side looks.
Yeah. Right.
All right. Great.
Okay. Gate delays. I'll separate it to 2 sections. First section and second section. So the first section is it takes 1 knot and 3 ends, and then it's going to add up to 10 gates delay. And then the second section is going to be the same thing, so it's going to be just 10 plus 10, 20 gates delay for every path except for the ones that never take NOT gates. Possible issues. There was just a lot of coding for especially test cases. A lot of common things. And then there was like many AND gates in my code. I feel like I could have done better with maybe behavioral.
Well,
or like
if you did behavioral, your code would have been kind of simpler, but maybe not better, because this one you
Okay.
actually specified instructional models. So
Okay.
it's good you chose that.
Okay. Because
Well,
I thought like I needed
and
to
then
take.
Verilog can do this. Yeah.
Right. I needed to take like 3 or 4 inputs in the same like for like one path, and then like I had to use like 3 AND gates for each path. So it was like just a lot of work, and I thought it was slow. There would have been a better way maybe. And then I think the real issue is that like every path it's going to take the same numbers of AND gates. There's no shorter way to complete the circuit for
Right.
any of the inputs. So yeah.
Yeah, that's fine. That's great.
Yeah. That's my presentation.
Any questions? Getting all excited. Okay. Let's go on. Okay. Yeah, all right. Yeah, let's just go. Thank you. You're gonna be next, Jonah.
Joking.
You sure you want to go next session?
I was prepared. I have it on my computer, a flash drive, and my GitHub, so you use whatever.
Do I need to do another pool?
It's in a little the PPT.
All right.
Joel, this homework better be easy.
Yeah, because I mean, I'm.
Well,
let's
Matt
welcome
might
our
be-
speaker.
Matt might be let down. I'll explain myself. Anyway, so I'm Jonah King, as nobody knows. My thing was the register file. And I thought it was very interesting. So basically, register file is just an array of processor registers, central unit. It can also be written to, read from. This is like a little structural thing, but this is literally like almost exactly like what I actually coded, because it made sense to follow the picture. So this is the actual code. It's very tiny, but so up here I have 2 registers, a thing that tells it which register to write to, the data I want to write, the switch that lets it know should I write yes or no, and then 2 outputs, and then 2 registers are 3 bits each. The output's 3 bits, so it knows which register I'm writing to. The switch is just the 1 or 0, and then I chose to do the 32 bits, just because I thought it would be better. I don't know. All right. So my data can be 32 bits, and then the 2 output registers are also 32 bits.
Well, you're supposed to, because you're supposed to match the implementation that we've discussed in class.
Yeah. And then I had 31 here, but you said it should be.
Which is 32.
Yeah. You should be here.
Did it work?
Yeah.
Okay.
Okay. And then instead of using the clock, I just used the always so that it would always do it. And then this checks to see like if the switch like is it on, then write it. And then put it to these. If not, don't really do anything. Implementing a testing. Find your lack of testing disturbing. Mm-hmm. Pretty awesome. Pretty awesome. That is my test cases, but I guess it would be better just to show you. I know, right?
Oh, and Verilog, that is always the case.
Yeah. So basically, I just did the register number, which register to write to, the data, which was very big because it could have been 32 bits, and then the output of each. So the first one 0. The first one, the outputs are both X because one, I'm not writing anything, and they don't have anything stored there. So it's like I don't know what you're trying to do. But for the next one, I actually wrote something to register 0 on both of them so that they both had a value. And then I just pretty much went down, and each one of these is which register to write to. It's I just did like a whole bunch of just different registers, and writing, not writing, just to make sure. And if I overwrote something, it would do the new one, like the new data I put into it. But if I just called like register 1 and I had already had register 1 up there somewhere, it just reprinted the number if I didn't do anything to it.
So you tested reading and writing, right?
Yeah.
Good.
Yeah. Yeah. Issues. I had a weird issue where I was printing out Z and I didn't know what that meant.
What does Z mean?
Unknown.
High.
No, it does not mean unknown. It means.
It means that it's not got any.
Hold on. Whoa, stop. Matt has got this.
High impedance.
High impedance.
Right, high impedance.
All right. Well, I googled it and that's what I saw, but I was like, I don't know what that means. I just went with something else. Wanting to hurl my computer at the wall in rage was also an issue. I had a weird. This is a different code that I used, but like one of my first like implementations of it, like it was taking forever.
Did you put a time scale on top?
Yeah.
That might be why.
Because it was.
Did your time scales match?
I think so.
Oh well.
I mean, that could have.
think so.
Yeah. Anyway, so it was. I waited like 5 minutes and nothing happened, and I was like, I can't do this. So then I like checked what was going on, and it was like, oh, I've still got like 30 quadrillion ticks to go. I was like, oh, I better kill that. And then etc. Just being angry and such.
And not being able to spell etc.
Yeah. Whatever. And 5 dots, 6 dots.
ECT.
I went with behavioral just because thought it would be more interesting, and Dr. West said that'd be sadness if I didn't choose anything else.
That's a car.
Because behavioral. Because I said what model? Get it? What model of car? It's a nice model. I chose a nice model.
Nice.
It's got to be like +5. And then just sources. I used Paul of the West, which is some weird guy on the internet.
That
guy. These dudes, register file, that's nice. I use GitHub, of course. And then just YouTube, watching various stuff just to get an idea.
Okay, alright.
And that's me.
What was the homework you were going to say?
Where's the homework, Jonah?
So I had this whole thing where I could click a link and it would pull up the PDF of Lab 3, and I was going to assign everybody one of the things on Lab 3, but due to the various restraints of PowerPoint, it did not happen.
So wait, PowerPoint just saved the class?
Yeah, it did. Because when I actually had it there and I tried to save it, it was like, something went wrong, and I can't save it. And then I was like, why? And so I Googled it, and somebody was like, yeah, if there's too much information in PowerPoint, it just blows up.
Awesome.
So I was like,
Okay, so any questions? All right, go back to your register file code.
Which one?
The short one.
The short one? That
There
one.
we go. All right.
I don't know why it's highlighted.
Always at star begin me.
It doesn't. It just means to like always begin there, right?
Yeah.
Yeah,
Like-
you always
The short
execute
is a
this
wild
code.
card.
Yeah.
If what would be a better thing to put there?
Just
Yeah.
initialize begin.
Well, initialize would only happen at the very beginning.
Okay.
Positive.
Pause edge of what? Clock, right. So this only happens on the pause
Putting a
edge of
clock
the clock.
Oh yeah. I tried that earlier, but like it was having a weird problem with the like the variable of clock, so I just got rid of
I
it.
just realized something. Have I never explained the reset line?
Nope.
No? Okay. That's fine.
Okay, good. Okay.
I'm just
realize
putting
there's a
notes
lot
of
of
what I
stuff
need
we
to put
didn't
back in Lab 3.
Oh,
Because
okay.
this class got rearranged a bit.
Yeah,
Okay.
we're
I
realizing a
obviously-
lot of stuff we're missing.
Or things get jumbled around sometimes. So, all right.
Okay.
We'll get to it. Don't worry. All right. All right. Any other questions, comments?
Concerns? Screams?
Nice
Ah. Okay.
That's all I got.
All right. Thank you, Jonah.
My pleasure.
Now, thank you for our final presenter. Is that right?
Mm-hmm.
You ready? You got this. You got this.
She's so excited. Come on, Ashley. You spelled her name
compared to everybody else. Did you really spell my name wrong?
No, I spelled Melina's name wrong. I'm
Oh,
sorry.
Yeah.
My
Well,
apologies.
you did forget my name, so.
Oh, that's true.
Oh, right. It could be worse.
You just forgot.
Your initial with your last name spells award.
I know.
I know.
Mine, the attachment email for ROTC is award.det.
All right.
No, I changed that. I just uploaded it.
Okay, hold on.
Hold it again.
Hold on.
Remove the old one.
Ignore Jonah. Yeah.
Just upgraded gold.
Oh,
There we go.
thank you.
I know. I saw everybody else do it, so I was like, I need to change
That
this
happened in
really
my
quick.
cybersecurity class. Everybody picked that one. And no, like one person changed the colors.
Let's welcome our speaker.
Yay. Good luck.
No. Compared to what everybody else is doing, I think I did this pretty wrong. But I'm gonna go with it. So I'm Ashley Ward. I chose ALU and the adder. And in ALU, it performs the normal arithmetic and logic operations, so like subtracting, multiply, dividing, adding, and then also the AND, NOR, XOR, and all of that stuff. And then it is considered the fundamental building blocks for the CPU. Wow, that's really messed up. And adder, it is the basic gate for the ALU, and it implements adding the addition of numbers, and there are two different types, the full type and the half. The half has 2 inputs and then 2 outputs, and then the full has 3 inputs, one of them being a carry in, and then it generates a sum and carry out, so 2 outputs. This is my code for the ALU. I put like one of everything in here, and then they all had different outputs. Pretty sure I did that wrong. And then this is my test case for all of it. And then for the half adder, it's an XOR and an AND put together. You'll see it in a minute. And then that's my test case. And then for the full, you have an adder, 2 adders, 2 XORs, and an OR. And that's my test case.
What is the test doing? Is it testing, you said it's just testing ORs, or I can't read it.
It's just testing each, like A, B, or C, like at all different variables that it could be.
Okay.
And then issues I encountered, I was going to do all of the like AND and NOR on each different file, and then I realized that would be way too much. So I decided to combine it all into one file so I wouldn't have to do so many tests, so I just have to do one test for the file. And then totally did your gates wrong, but this shows what each one is.
Okay.
Yeah.
Ooh, whoa, go back one? I kind of like that one. I mean, it's not a or, but yeah, I like it.
It's the only thing I could find that kind of went with it.
like it.
So,
I like it.
well, you
I
should
like
see
it.
the XOR. It looks kind of funny.
Okay.
I didn't know how to do it.
You know, I should have like I just saw Back to the Future where it has all the extra lines going back.
Yeah.
That's what she did.
NOR, and then this kind of shows the half gate. So you have A and B going into an AND, which creates C, and then A and B going into an XOR, which creates S. And then the full one, this one's kind of confusing. You have A and B going in an XOR, and then you have A and B going into an AND, C and the XOR from A and B going into an AND, and then these 2 ANDs make the C out from an XOR, and then this XOR and C makes the S.
So, okay, that's the, I guess you
At least
added
it's
all the
color
gate
coded.
delays, but
I
what's the
tried.
gate delay of the circuit is the question.
Yeah, I did that wrong.
Well, let's go look at it real quick. So
I'm honestly, to be quite honest, I'm still confused about the gates.
Right, so let's do it. Alright, let's help Ashley out and do this. Alright, so which ones are taking 4 gate delays and which ones are taking 3?
XORs are 4.
The
ANDs are 3.
yeah, these are 4 and then these are 3.
Alright, so what is the critical path, aka what takes the longest to get through?
Oh, this one.
So to get to the S, well, you only need to go through 2 XORs, right?
Yeah, that would be 8.
Right, so that one's going to be so S takes 8 gate delays to get to. Okay? How long does it take to get to the C out?
Do you add both of these together since they're parallel?
They're parallel, so you just
don't?
take whatever
It'd be
what
7.
took longer.
But you have an or and
No,
then
'cause you have the
2
XOR
ands,
first
and then
for-
an or again. I mean, an or.
From A and B.
Yeah,
So-
I didn't see that.
Yeah.
Yeah. So,
Okay, so
think of it going in reverse.
11.
Okay, you have to do 4 here no matter what, right?
Mhm.
And then it's, okay, 3 here, so that's 4 plus 3, so 7. Okay, that one's done, so this path is only 7. And then this one, oh, there's another one right here, so it's 4 plus 3 plus 4, which is 11. Right. So,
Okay.
and so C out takes 11 gate delays, and S takes 8. So you take the one that's larger because that's critical path, therefore it's 11.
Okay.
Make more sense?
Yes.
All right.
And then those are my sources.
All right. Any questions? Whoa, whoa, whoa.
He's always got questions.
Whoa. I'm terrible. Well, I just gotta make sure you learned it or you learned whatever.
You learned something.
Gotta learn something.
You want to see something
Okay.
funny? It says my name spelled wrong. I couldn't fix it.
Hey, it's all downloaded in paper. Well, let me fix the E real quick.
Wow.
There we go. No, I wrote an E, but it looked like an I when I wrote it.
Oh.
It doesn't make any sense.
Can't do your name.
Okay, go back to your ALU. Hit F5.
That one?
Yes. So the ALU is supposed to do NAND and add. Because we have not and or NAND XOR. Did you address doing an add? I thought I saw half adder and full adder.
What?
Well, the adder is supposed to be part of the ALU because the ALU can either do one of those or an add. That's okay.
I don't know what you're talking about.
And then your ALU, it looks like it does only 1 bit. Is that correct?
I believe so, yes.
Yeah. Okay. So it needs to do for 32.
I don't know how to change that.
It only has to do NAND. It only has to do NAND and add are the two operations.
So take out everything but the NAND and the
Right. Take out everything but the NAND, and then get the adder in there somehow, and then increase it to 32 bits.
That is a lingo. I have no idea.
Yeah, I don't know how to increase it to 32.
Okay.
I can take the everything up in the NAND and add, but
So how would you increase it to 32? What would you?
I don't even
so you
know
have
that I have
inputs. Right now they're 1-bit wires, so just make them 32-bit wires. So you would add a 31 to 0 after them.
after these?
Yeah. No.
After the
I don't know what you're talking
output?
about. I'm sorry.
So you see this right here? Oh, we're gonna put black on black. This will be beautiful.
So you do that for your two inputs and not for your carry-in?
Well, yeah, exactly, because you have your inputs in a sub. Sorry, I'm in your way. 31 to 0. And this needs to be
that's
solid.
a curly brackets.
I made it solid. Yeah, one day I'll get better. I should just use the markers Caitlin gave me. because
Yeah.
They work, right? All right.
Wow, that's a parentheses.
You just can't do a closing bracket.
All right, so then both A and B are inputs.
Yeah.
Now you would have your carry bits inside of it, but with your ALU you don't care about the carry bits at the end. You just want to know what the answer is. So your out, you have some outs right here, but you probably want. Oh, I don't know why I drew an S. So we'll just say NAND out 31 to 0.
Yeah.
And then add out 31 to 0.
Okay. And then you'd have 32. 32 NANDs? No.
Yeah, you just have 32 NANDs for each of the 32 bits, and then that add out, you'd have to do the carry adder and just hook them all up. You have the full adder, so just hook them up in parallel for each bit, and then
So you'd have.
Let's get this going, okay?
You'd have 32 NANDs and 32 adders.
Full adders, right? And then that final carry bit that comes out, you don't care about.
So you don't output.
Yeah, you don't output that. Now, in reality, this is actually just a regular wire, because if you looked at the ALU, you only had one output. Whoops, 0. And it's hard to write that from this way. And what you do is, remember, you have that line coming in that's telling you whether it's an add or a NAND, and that would be hooked up to a MUX with these two guys as inputs, and then that guy is the output, and that selector bit is just selecting which of those two to output at the end.
So for our ALUs, were we supposed to implement a MUX?
You're supposed to use a MUX, yes, or at least use one. You didn't quite get that, but really I would have accepted this up here without the final output because you're only doing the ALU and the adder. You may want to take a picture of this. Okay. All right, let's go ahead and thank our final speaker.
Yeah, now you can help us with our fixing our.
Okay. Let me go.